Yes. Yeah. Hello. Good morning, everybody, and welcome to this Horizon Success Stories event at the 6th edition of the Raw Materials Week. We will start with a welcome and open speech by Mr. Henning Ehrenstein, Deputy Head of Unit in DG GROW, Raw Materials and Energy Intensive Industries. Mr. Ehrenstein, the floor is yours.
Thank you very much, and good morning, everyone. A warm welcome to this new iteration of the Raw Materials Week and this particular panel on success stories that we want to share and discuss. It's a great pleasure to welcome you here virtually in Brussels, given the COVID situation today. I hope that the presentations and sessions that you will attend during the week will bring you a lot of practical knowledge, a lot of connections with potential partners, new exciting business opportunities for your future projects. Raw materials are, of course, crucial for us achieving the Green Deal objectives and making the green and digital transition happen. If you want, they're the base for all the industrial value chains and just fundamental for green and digital technologies. So the EU Green Deal recognizes the access to resources as a strategic question for Europe. That's also against the bottleneck of the COVID-19 pandemic, having revealed many bottlenecks in EU supply chains. We've been experiencing supply chain disruptions leading to shortages, price pressures, as we know, on metals and minerals, and also on wood. Recent Commission analysis on strategic dependencies confirmed that the EU is highly dependent on third countries for certain raw materials, and a large part of these identified dependencies relate to raw and processed materials and chemicals for the energy-intensive industries in particular. The EU COVID-19 Recovery Plan 2020, including the Recovery and Resilience Facility, together with the Action Plan on Raw Materials of 2020 and the updated Industrial Strategy, all aim at addressing these strategic dependencies and fostering the green and digital transition. This will involve developing more resilient value chains for our different EU industrial ecosystems, improving circularity, resource efficiency, strengthening sustainable and responsible domestic sourcing and processing, and diversifying supply with sustainable and responsible sourcing from third countries, and strengthening rule-based, open and undistorted trade in raw materials. Research and innovation is an important element for the EU policy on raw materials, and specifically the Critical Raw Materials Action Plan adopted in September 2020. Over the period 2014 to 2020, we have channeled around 600 million euros into raw material related research, developing technological and non-technological solutions for the entire value chain, from exploration, extraction, processing, recycling, and for developing substitutes for critical raw materials. We will continue our efforts in the new program, Horizon Europe, where we, under the first work program, have devoted around 300 million euros for raw material actions. What you will hear today are prime examples of projects financed under the previous framework program for research and innovation, that's Horizon 2020. The projects financed under Horizon 2020 form a valuable base on which we will form our further research and innovation program, Horizon Europe, fitting into a more strategic way of thinking about raw materials in line with current geopolitical realities. So to conclude, I'd like to thank the colleagues from HDR for all the work the project managers have been doing over the years and for their presentations today. We are happy to have them all here as these projects are really the results of our work programmed over many years now. So it will be very interesting to see the results and have them presented here during the week. I hope you enjoy the session today and the rest of the week. Thanks a lot for joining.
Thank you, Mr. Ehrenstein, for this inspiring speech. I would like now to give the floor to Victoria Petrova, Head of Unit Industry in the Health and Digital Executive Agency of the European Commission, HADEA. Victoria, please, the floor is yours.
Thank you very much. Hello to everyone. Sorry, it's the kind of things that happen when you try to come to the office and connect from a safe network, but it's never safe enough. Sorry for that. Hello to everyone. Very happy to see you here for the Raw Materials Week. And now for this specific session on technology success stories. So thank you very much for your presence and for this online connection. And welcome indeed to the EU Horizon Technology Success Stories that we indeed co-organize between DG GROW and HADEA that are parts of the European Commission. Throughout the day, we want to offer you a first-hand account of the latest EU-funded research and innovation. So as you might know it, in this, HADEA is an executive agency on health and digital, and industry is part of it and includes raw materials. Thus, you will hear about the selection of projects under Horizon 2020 that are bringing tangible advancement to the raw materials area. As you know, European industry is one of the cornerstones of EU growth and competitiveness. And in turn, raw materials are crucial to many European industries. They're at the cornerstone of the European industry. Simply said, raw materials are essential input for the competitiveness of industry and the development of many environment-friendly, clean technological applications. And the current pandemic has shown that Europe must shape and reshape its value chains, including the raw materials, and the ability to autonomously source and access minerals and metals, including critical raw materials and other high-tech materials. So we have all seen the level of dependency that we have. If I just mention semiconductors, this will ring a bell clearly to you. So why it's important, why it's key? It's a matter of competitiveness of Europe, its industry. It is essential to deliver more resilient, more green, and more digital recovery. And it is essential also to minimize the environmental impact, the impact on environment that is what we will let to our children and grandchildren, and to mitigate risks linked to raw materials sector. For this reason, in the past 7 years, in the period of 2014-2020, the European Commission has invested over €500 million, more exactly 570 million. It would have been good to have 700, but unfortunately it was not the case. But we are moving towards. So 570 million invested in raw materials projects, mostly for technological research and innovation. So what does it mean? For Horizon 2020, that we have still ongoing running projects, 91 projects were dedicated to this topic. Among the participants, as you would see on the pie chart that is in front of you, we have 45 persons that are private companies, and almost half of them, 47%, are SMEs. To make it a balanced mix, research organizations represent close to a quarter, almost 20%, and 16% are higher and secondary education organizations. So as you see, it's a very good mix between industry and research organizations. Participants are also well distributed over Europe. It does not stop at EU borders. Indeed, you know, Horizon 2020, and as now we are rolling out Horizon Europe, will be and are programs that involve international partners. And we have 52 participations in third countries outside the EU. What we want to address is a number of significant challenges along the raw materials value chains. Developing advanced solutions for substitution, indeed, on those critical raw materials that are essential and we have high dependence on imports, it's important to work on substitution and greater resource and energy efficiency. Indeed, how we can do more or the same, but with less input of energy and less input of resources. And we need to ensure effective reuse and recycling. We're talking about circular economy. Clean primary production of raw materials, including critical raw materials. No one wants to have dirty mining. We have all in our minds the image of the miner with his black face. This is no more the modern mining and raw materials industry. Now, let's start upstream and talk about exploitation in the value chain of raw materials. I think the slide shall be changed. Yes, this is the slide on the participation from third countries. You see, no, already in the EU, you see we have a utmost champion with Spain and then Belgium and Finland. So we're going from the south to the north of Europe, and we have great distribution. And then you have the part that indicates that Norway is extremely involved in the projects. And you have also the map with the distribution, geographical distribution. Next slide, please. This is the participation in third countries. You see we have our favorite participant, champion is South Africa. One could imagine that South Africa is particularly rich in raw materials. Therefore, this justifies, this is the rationale for such a high participation. Next slide, please. So let's go about the value chains. So we need to lower the cost and expand the reach of exploration activities. For that, we need high efficiency and cost-effective sustainable exploration technologies. Let me give you an example of 3 very successful projects. You see the names and the logos.
We have lost the sound.
Is that right now good?
Mm-hmm.
Yes. Okay. Sorry. So I was saying that I will give an indication on some of the projects in the area, and I will start with the upstream. And here I will start with the Pacific, which is not the ocean, as I said, but a project on raw materials. It has developed a low-cost and environmentally friendly tools for exploring mineral deposits beneath the surface, underground. This is an increasing demand in the mineral exploration industry for subsurface, underground imaging of high resolution. Smart exploration has addressed these needs. The project has produced cost-effective and innovative exploration instruments comprising airborne, surface, and downhole and in-mine modular-based geophysical systems. Now, let me talk, that was the second project. And now let me mention the project that is called Infact. It has developed innovative geophysical and remote sensing technologies. The project has used a helicopter, a fixed wing aircraft, so that was over the surface, and a selection of unmanned aerial vehicles to acquire the data. Now, let me move forward to the extraction step in the value chain of the raw materials. New deposits are small and complex to access and located at deeper locations or more extreme environments. This can jeopardize the technical and economical feasibility of mine deployment and operations. Novel mining solutions, new approaches are required to access these unexploited deposits. They should be sustainable and environmentally friendly. It is also important to integrate them with the processing step in the economical viable process. A few excellent examples are, to give you some indications, one of those is the project called Impact. And it has demonstrated a novel approach, a mobile modular containerist plant for selective and low impact mining of small high-grade deposits that make viable the exploitation of small complex deposits. So it's a matter of accessibility and exploitation. Then we have X-Mine that has a pilot project on intelligent mining system with integrated sensing technologies based on X-rays analysis. These are some examples of developments that improve efficiency and sustainability of mining operations. So now let me, ladies and gentlemen, go a bit further down the value chain and tell you about the new processing technologies for waste polarization. As I mentioned, we were speaking of circular economy. They can unlock unexploited EU resources. Instead of importing new resources and processing them, it is a matter of recovery. The objective here is to recover raw materials in domestic EU byproducts, mostly unexplored in the past due to their complex composition. It's very complicated. You have one of the pictures that is illustrating the level of complexity of some of the technical components. We have 4 excellent projects developing material and cost-efficient processing technologies. So you have the one that is called Secrets. I think tomorrow we will hear more about them. It establishes processes to extract, separate, and transfer rare earth materials to their application in electric vehicles, industrial motors, and wind turbines. This term rare earth will be the one that is guiding us through the next coming decades, I would say. Removal, that is another project and not just a verb. It strives to remove waste streams from the primary aluminium production and other metal sectors in Europe, an example of a more sustainable and resource-efficient industrial process. And Nemo, this is not just the fish, as you can guess, it focuses on near zero waste recycling of low-grade sulfidic mining waste for producing critical metal, mineral, and construction raw materials. So there is a fish in the construction. So, and here we have another very good example, Platarios. As you can guess, it's connected to platinum, coming from the title of the project. It has demonstrated platinum group metals recovery from spent autocatalysis in 3 consecutive steps: leaching, separation, and recovery. Finally, to support the recycling and to reduce the pressure on demand for primary raw materials that we have stated is one of the key objectives of increasing autonomy and reduction in dependence on third countries' imports. We need to support recycling and to reduce the pressure on the primary demand, as I said. So we have granted 48 million, almost 50, for the coordination and support actions during the last programming period. We're speaking of the 2014-2020. So you have the projects that are called collectors. That is a project focused on local good practices for municipal waste collection. You know very well that the collection and recovery of waste is starting with the municipal, local, and regional level. And it would lead, this collectors project will lead to high quality recycling. Data has been collected, analyzed, and disseminated during 3 years to provide a very robust database and baseline. Another example is the sea waste. It focuses on we. So we is not the tablet you play with. It's about waste from electronic equipment, as you know, and batteries. That contains, so this project, it focuses on this we, and it contains significant amounts of valuable and critical raw materials. So the project Sea Waste has developed a voluntary certification scheme for their collection, transport, and treatment at waste facilities. And this is not all. Altogether, 312 million euros are to be granted for the period 2021-2022. Here we speak of the new programming period with the new program Horizon Europe. We will meet tomorrow afternoon, 16th of November, for the Horizon Raw Materials Info Day and Brokerage event. We will discuss upcoming funding opportunities, current analysis, and upcoming opportunities. And in particular, we will dedicate some time to the Horizon Europe raw materials dedicated calls and topics. These calls are already open and will close at end of March 2022. So please spend that in your agenda. 31st of March 2022 is the last moment, last chance you can submit an interesting and valuable project that will make the difference for the next programming period. Our primary objective with today's event is to inform you about the most recent advancements in raw materials technologies. But beyond that, we expect to inspire you, to give you indication, orientation, and ideas. I would be pleased to see that you shape the most ideas into excellent projects for the 2022 calls with your proposals that we expect seeing there. That way, we can continue tackling together the technological challenges along the raw materials value chain. And here I will stop and give the floor to our wonderful moderator. Thank you very much for your attention.
Thank you, Victoria, for the great overview of the event and the developments in the field of raw materials overall. I would like now to give the floor to my colleague Veronique Vaule-Ebongue, who will be chairing the session on securing the supply of raw materials in a sustainable and responsible way. Please, Vero, the floor is yours.
Thank you, Yol. Good morning, ladies and gentlemen. It's my pleasure to welcome you all to the first part of the session on technology success stories. This morning, we will talk about mineral exploration and extraction only. The rest the rest of the presentation will be given this afternoon. We will see how the 5 EU-funded projects selected to give a presentation this morning have replied to the challenge of securing the supply of primary raw materials in a sustainable and responsible way. The work of the 3 first projects selected, as Victoria said, Pacific Smart Exploration and Infact have focused on exploration, while the last 2 projects, Impact and X-Mine, is on extraction. The 2 last projects will be presented after the coffee break. So each speaker, kind reminder, will present the main result of their project during about 15 minutes, followed by the possibility to answer a few questions directly after each presentation. So to the participant, you are kindly requested to post your question on Slido. You can access Slido from any browser or device using the event code. Some of your questions will be taken and asked to the speakers after their presentation. So we will have a 30 minutes break after 11:15. This break is aligned with the coffee break of the critical raw materials event taking place at the same time. So now we will start with our first speaker, Nicolas Arendt, who is also one of the scientific coordinator for the Pacific Project. He is Emeritus Professor of Petrology, Geochemistry at the University Grenoble-Alpes in France, and director of the CISPROB company that uses ambient noise seismology in mineral exploration. He has held academic position in the United States, Canada, Australia, and Germany, and has worked in the mineral industry. His main research interests include petrology and geochemistry of mafic and ultramafic rocks, origin of the continental crust, the early Earth environment, magmatic ore deposits, and future mineral resources. Nick, please, the floor is yours.
There we are. Now you should be able to hear me. Is that fine? The image is a little blurry, but is this okay? Can everybody hear me? I see nods. Okay.
Yes,
so
we do.
So you will show the slides. There we are. So I'm speaking on behalf of the about 33 members of the Pacific team about the Pacific Project, for which the aim is to develop environmentally friendly and cost-efficient mineral exploration tools. Next slide, please. So here's some information about the consortium. There are about 9 members with some sub-members from universities, from research institutes, from the Geological Survey Ireland, and from private companies. And on the left, you see some information about the cost and duration. We have 2 test sites. One is in Canada, labeled 3. This is the Marathon Platinum Copper Deposit. The other is in northern Sweden, the Kallak Iron Mine. Next slide, please. So what are the objectives? The objectives are to develop new techniques, new passive seismic techniques, and I'll show you how these work in coming slides. Now, the problem with current methods is they have a relatively low spatial resolution. The results we get are not very precise in terms of the position. So we tried to develop 2 techniques to improve the situation. One is to extract what we call body waves from the ambient noise signal. The other is to use a multi-array system to try to resolve this problem. And in addition, there's another aspect, which is to look at the social acceptance and public perception of mining activities in general. Next slide, please. So how does it work? In this image, we see what we call receivers. We call them nodes. They're autonomous seismometers, which we place at the surface. Each receiver records the seismic signal coming from below. An adjacent receiver also records the same signal, and by comparing the differences in the two signals, we can get some information about materials in the subsurface. Specifically, we record the seismic velocity of materials in the subsurface, and this gives us information about the lithology and structure beneath the surface. Next slide, please. So how does it work? On the top left, we see one of these receivers. They're small, they're autonomous, they have a battery, they can record for 30 days or so. They can be carried in a backpack to be deployed, as we see in the top right, and they can be deployed in areas without a need to construct roads. So it has a relatively low environmental impact. On the bottom left, you see a typical array. We deployed maybe 200 receivers in a more or less rectangular array. Next slide, please. So the first test site is Pacific. You see the locality in Ontario, north of Lake Superior. And there we deployed a very large array of 1,000 nodes. On the right, you see John McBride from Generation PGM, who is the operator at the site and who gave us tremendous support for this operation. Next slide. So we'll see if we can run this. This should be a video. And can we run it, or would you put the video in its place?
Ambient noise seismic wave tomography study of the Marathon platinum group element copper deposit. The Marathon deposit is on the northeast rim of the Caldwell alkaline complex. Generation mining explored by drilling the gabbros that contain the mineralization. Archean metavolcanics underlie the complex. Most of the complex is made up of main stage gabbro. The Two Duck Lake and Marathon series gabbros host the mineralization. Cyanites are the uppermost unit of the complex. We did a passive seismic survey of the deposit with an array of 1,000 seismometers recording for 30 days. Noise sources were storm waves on Lake Superior, waves in the North Atlantic, and freight trains. The aim was to image the lower contact of the intrusion, which controls the mineralization. Most drilling is limited to 400 meters. Our surface wave tomography allows us to see much deeper. Here, we see a seismic anomaly model. Red is fast and blue is slow. These are horizontal slices through the 3D tomographic model from near surface to 2 kilometers depth. Now we compare the velocity model with geology. We use the contrast in velocity. Gabbro is fast, syenite is slow, and the footwall in green is intermediate. In this cross-section, we see the geological model of the mineralized gabbro in purple. This tracks the lower contact of the intrusion, which is defined by a jump from fast to slow velocity anomalies. Passive seismic is helping Generation Mining to plan their drilling and reveals the deep plumbing of the Caldwell alkaline complex.
Okay, that's fine. Now if we can move on to the slides again. So this is the main result of the surface wave tomography. We were able to image the lower contact of the intrusion that contains the mineralization. Next slide. And we also found that there are different types of ambient noise, but we found that the freight trains on the Canadian Pacific line provide an excellent auxiliary source of seismic noise. And next slide, that's fine. And we had another result, which was we were able to measure seismic anisotropy, which tells us the differences in the velocity of seismic and noise according to the direction. So this anisotropic data, as you see on the bottom slide there, C shows that the anisotropy is parallel to the contact of the gabbro, adjacent to the gabbro, more random away from it, which provides additional information which we can use to determine the characteristics of the subsurface. Next slide, please. The second test site was Kallak, an iron ore prospect in northern Sweden. Next slide. Here we tested the multi-array approach in which we deploy receivers at the surface and downholes. And we'd additionally planned to use ongoing drilling as an additional noise source. Next slide. So here we see the operation. In fact, this whole operation was severely disturbed by the COVID problems. We'd intended to do it in the summer of 2020. This was not possible, so we did it only in August of this year. So far, we only have preliminary results. On the left, we see deployment of the sensors down drill holes. In the middle, we see the surface array, a relatively large surface array, and we used an external source of noise. So if we can show the next video right now, a short one. Okay, so that was just Anais. She's one of our geophysicists dancing along between a compressor, which provided additional noise, which we captured using the surface array and the downhole array. Next slide, please. We have preliminary results, and basically these results showing we're capturing the signal in the surface array, and we're seeing signals bouncing back between the surface and downhole arrays. So these results are promising. Next slide, please. We conducted other surveys at other sites in Las Cruces in Spain in collaboration with Infact, in Kaiserstuhl in Germany, in collaboration with the company TerraTech and High-Tech Alcab, H2020 project, and in Silver City in Germany, in collaboration with Exelon, a company, and also Infact. Next slide, please. The other aspect, the important aspect of our program was a series of questionnaires and computer experiments designed to assess public opinion of mineral exploration, specifically in Ireland, but the techniques could be applied elsewhere. It was done by Aoife Braden in the Geological Survey and Olga Perevskirova in the ESRI Behavioral Unit. They conducted surveys, questionnaires, and also assessed the results of these questionnaires using in such a way as to better understand why people answered and how they answered. Next slide. So next slide, the general results, the conclusions are here. They found that a significant proportion of the people do not have a strong opinion about the development of new mine. There's a slight majority who had more positive than negative opinions, but there are specific aspects of that. There are clear conclusions concerning how to communicate information about mining activities, and it was found that national organizations like the Geological Survey or the media need to provide clear, objective, accessible information. It's important to send this information early on, because the surveys found that first opinions had more impact. It's also important to try to communicate more about the positive aspects, the benefits of mineral exploration and mining, the need for metals, the need for primary production. And yeah, so next slide, please. So these are the conclusions. We have to say that at Marathon, the first site, we had only limited access in extracting body waves from the ambient noise signal. We got some results, but we didn't really succeed in developing a tool that could be used on a practical level for mineral exploration. However, at Kallak, the preliminary results from the multi-array method are very promising. We found ways of providing what we call opportunistic or accessory noise sources, which greatly improve the technology. And finally, surveys of public perception provide valuable information about how to communicate on issues related to mining and mineral exploration. Next slide. Okay, so that was just the contact information. That's it. Thanks very much. And I'll wait for questions, which will happen, I'm not sure, even now or at the end of the program, at the end of the session. Veronique, is it now or do we go into the next slide?
Thank you, Nick, for the very nice presentation, very clear. Thank you for the very clear videos as well, and your point on public perception and communication with the local community in order to raise awareness, of course, about raw materials, the raw materials need for our industry. So we should maybe take the time for one question. Maybe Victoria, do we have a question for Nick at the moment? It seems that we do not have any question from the audience. So, Nick, we will have the panel discussion at the end. So you will get questions there. It will be moderated by Marco, our colleague. So please, thank you again. We will move to the next speaker, Laura Valentina Socco. I know her more than Valentina, than Laura Valentina. Good morning, Valentina.
Good morning. Thank you.
Good morning. Valentina is full professor in applied geophysics at Department of Engineering of Environment, Land and Infrastructure of the Politecnico di Torino in Italy. Valentina works on developing geophysical techniques for near surface investigation in application ranging from seismic hazard and engineering to hydrocarbon and mineral exploration, environment, and also cultural heritage. In the past 20 years, she has focused research work on surveying techniques based on the propagation of seismic surface waves for estimating subsurface velocity models and on geophysical data integration techniques. She is an author and co-author in more than 150 publications in peer-reviewed journals and conferences. She's chair also of the education program in environmental engineering and of petroleum and mining engineering of Politecnico di Torino since 2018. In Smart Exploration, the successful story, Valentina has been co-leader of Work Package 1, dealing with the management of the project, and leader of Work Package 3, modeling and processing method. Please, Valentina, the floor is yours.
Thank you very much. Can I have the slides, please? Thank you. So what I'm going to present you is basically on the behalf of the whole Smart Exploration group, and in particularly of the executive board of the project. Next slide, please. So maybe this slide is a little bit superfluous considering what have been said at the beginning of the session today, but I just would like to stress that it's really good time for a project that aim improving our capability of exploring the subsurface, because catching up with our capability of mapping and exploiting EU raw material resources is of paramount importance for our ecological transition and the carbonization process. So let's say we really feel that a project like Smart Exploration is on time in a certain sense. Next slide, please. So Smart Exploration, there are some differences between the slides I I see, but okay, the logo is not there, but it doesn't matter. So the Smart Exploration was a pretty large project with 27 partners coming from 9 European countries and a quite broad distributions in terms of roles, let's say. So we interpreted a little bit the call, which is research and innovation actions, in a 3 pillars project, where both research, innovation, and action are a pillar itself. The consortium was pretty, let's say, pretty broad also in terms of kind of partner. There were 11 R&D partners, 11 SMEs, and 5 stakeholders. The project was a 3-year project, started in December 2017 with a budget of 5.2 million. Next slide, please. So what are the pillars? Well, Smart Exploration had the objective since the very beginning to create tangible results. And the tangible results had basically 3 main pillars. The first one was we have data, not only new data, but also legacy data, a lot of legacy data. And we are now able to interpret and process those data in new ways that improve the amount of information that can be extracted from the subsurface. So we wanted to also stress on the value of the legacy data and their integration with new data. Then we worked on the development of tools, new measuring tools to improve our capability of exploring the subsurface by developing several new prototypes of instruments that were developed, engineered, tested, in some cases patented, and brought to the market. Then we wanted also to improve methods. So we produce new codes and algorithms and workflows for improving the effectiveness of the processing and the interpretation of the data. And all these 3 pillars were made possible by a young professional group that was extremely active, vibrant, and interconnected. Next slide, please. We also had 5 sites all in Europe, 5 pilots, one in Portugal, the Neves Corvo mine, one in Sweden, the Bottleberg deposit close to Ludvika, then Silinjärvi mine in Finland, Gerolakas in Greece, and a greenfield area in Kosovo. And we, let's say, in this way, covered a pretty wide range of commodities and also exploration challenges coming from completely different geological environments. We worked on all this side by using both vintage data and also by acquiring new data sets that were aimed at validating both our acquisition tools and our processing and interpretation new methodologies and workflows. Next slide, please. So let me give you an highlight on what were the results at large, let's say. The project provided 47 deliverables by the end of November 2020, which were reports, calls, or mainly reports, let's say, and produced also during the duration of the project more than 100 peer-reviewed publications. And these included also 3 special issues of journals and magazines that were produced specifically for the results of the project. there were more than 100 presentations made at major conferences basically all over the world, because we covered EU, Canada, Australia, South Africa, Asia Pacific, in many important conferences, both specific for geophysics and more general for mineral exploration and production. The project was based on 38 milestones that were met by the end of the project, and also more than 10 workshops were organized on the basis of the smart exploration results in several international conferences and symposiums around the world. 2 patents were filed, 2 pitches, and also 1 trademark in EU was deposited. We had more than 30 young professionals involved in the project, with an amazing gender balance, by the way, and with a very strong interconnection among the young professional group. Many of them are already in the job market. We produced 8 master theses and 9 PhD theses. 2 of those PhD theses got special mention. The project also was honored to receive the SEG Distinguished Achievement Award, and several commercial works were started already during the project. Next slide, please. Let's start from the prototypes. 5 prototypes were produced. The first one is a GPS signal system that is able to carry the GPS time at the microsecond accuracy in a tunnel, in a mining tunnel. Then we produced an innovative seismic vibrating source. We produced 2 EM systems. One is a low frequency time domain airborne or helicopter-borne EM time domain system. Another one is an UAV ground-based and UAV-based system that is both EM and MAG. And then last but not least, we also produced a slim borehole system, which is innovative because it makes use of fiber optic to allow having a very small sensors that can be deployed in the classically extremely slim exploring holes which are made in mineral exploration. Next slide, please. So the electromechanical broadband seismic vibrator that was designed and engineered together by one of our SMEs, Seismic Mechatronics, provides a very efficient and very high quality and broadband data. We used it in several of our acquisition with data of extreme good qualities, and we also had the opportunity of comparing it with other more classical vibrating or explosive sources, demonstrated that the data are more broadband and more controlled. Next slide, please. The GPS time synchronized geophysical surveys is also a very innovative tool, because it allows to synchronize a seismic acquisition that is carried out on a deep tunnel with a seismic acquisition that is contemporarily carried out on the ground surface. Next slide, please. Here we see an example in the Neves Corvo mine in Portugal, where the E-Vibe seismic was carried into a deep tunnel of the mine, and data were acquired contemporarily in the mine and on the surface. Next slide, please. in order to improve the knowledge about the extension of the mineral deposit. This is a pretty unique data set, which is still under processing. There are already a couple of publications and significant results, but a lot can be still extracted from this unique data set. Next slide, please. The helicopter-based deep penetrating time domain EM is a low frequency because it's 6.25 Hertz operation system, which is lower frequency than the usual time domain airborne systems that allow a deeper investigation depth than the usual one by keeping a very good resolution in the shallow targets. This also has been adopted and data have been acquired in several of our pilots, including greenfields. Next slide, please. This is the ground-based and UAV-borne EM system that is a new UAV-borne system that carry out both magnetic sensor and EM sensor that is connected also to the ground-based system, which is still, and the UAV system travels over the fields. It allows us in an extremely fast and cheap mapping of large areas. Next slide, please. And this is our slim hole seismic acquisition system that, thanks to the use of fiber optics, is able to reduce the size of the sensor, which are lowered in the well, allowing to exploit the small size boreholes to perform geophysical acquisition at depth. Next slide, please.
Valentina, 2 minutes.
Yeah. As I said, we also developed new processing methods. Seismic was one of the focus. We developed several methods for improving the near surface velocity models that are used to improve the quality of the deep image. And we also developed new seismic migration for 3D exploration data to improve the resolution of the targets at depth. Next slide. We also applied passive seismic data quite a lot. Nick already introduced very well this data. We did several applications by using both high frequency and low frequency passive noise, both using surface wave and extracting body waves. On the left side, you see a comparison between an active seismic line and a passive seismic line when you can see some real reflector appearing from noise data. Next slide, please. Processing and interpretation method were also developed for EM. A thin sheet code with IP response was developed for 2D data, and a full 3D TEM inversion was developed as well. Next slide, please. Among our, let's say, results, we also had new potential targets. All our sites were explored, all the vintage data available were integrated with the new data, and in all our pilot, we were able to increase the knowledge about the mineral deposits that were now exploited. Next slide, please. We made a lot of dissemination work and civil society engagement, particularly at Ludwika Commune, which is close to the Ludwika mine, involving in our job all the population, starting from primary school children to retired people. And it was a very interesting experience of, let's say, culture and scientific knowledge transfer also to the local community. Next slides. As I said, we published 3 special issues on geophysical prospecting and first break based on the results of the project. Next slides. And what is the life beyond? Well, I think we showed some good convincing practice. Innovation was certainly clear in the project. The reviving of legacy data is also a strong message, and many of all our job were really focused on how to solution approach. And then, of course, the young professional teams that you see there was really a great resource of our project. And I think that's all. I don't know if there is still one slide, but I think that is all.
Thank you, Valentina. Thank you very much. Thank you for providing us with the very impressive achievement done by the Smart Exploration project. You and your team members, co-members, consortium members went far beyond the expectation for research and innovation, a 3-year duration research and innovation. So thank you very much. It was very impressive and very knowledgeable team, of course.
Thank you, Veronique. It was great fun, by the way. Not only hard work, but also great fun.
Extremely hard work, I imagine. Thank you. We do not have any question yet on Slido, so unfortunately we will have you will have to wait together with Nick for the panel discussion after the end of or at the end of the presentations. Now we will go and switch to the next presenter. Sarah, are you ready? Sandra Lorenz, my apologies, is a researcher at the Eltmos Institute Freiberg for Resource Technology since 2014. She received the doctoral degree, Dr. Remus Naturalis, I am right? I'm saying it right, yes, in geosciences at the Technical University Bergakademie Freiberg, in Germany in 2019. Currently, she is head of the digital processing group within the Department of Exploration of the Helmholtz Institute Freiberg. Her research focuses on the EAV-based terrestrial and lab-scale hyper spectral imaging for non-invasive mineral exploration, in particular, multi-source data processing and integration. Please, Sandra, the floor is yours. Okay, you are also a part of the Infact Horizon 2020. You were part of the Infact Horizon 2020 project team. Please.
Thank you very much for the nice introduction. I hope you can all hear me very well. Yeah, I would just think that's like that. I saw that I need to hurry a little bit, so I will do my best to keep up to the time. Yeah, wish me luck. Yeah, so I would start right now. And I would like to discuss today with you how can we shape the future of mineral exploration in the EU, and how did the Infect Project, which stands for Innovative, Non-Invasive and Fully Acceptable Exploration Technologies, contribute to this goal and to move towards a more sustainable and socially acceptable exploration in the EU. The next slide, please. The Infect Project consisted of 17 partners, all over from research and academia, from mining industries, from the public sector and non-profit organizations from all over Europe, and they joined forces to tackle several goals to go towards more sustainable exploration. 3 of the main goals were to support the development of non-invasive exploration technologies, to make sure that all the stakeholders' voices are heard, and to look worldwide for best practices to apply in the EU to go more towards these goals. The next slide, please. A fundamental pillar to achieve these goals was the setup of 3 European reference sites. They are located in Finland, Germany, and Spain. And they were carefully selected to cover a broad spectrum of different aspects. So, for example, a broad geological context, so in terms of deposit type, host rock, cover thickness, and geophysical parameters. also of environmental factors, so of different climate and, so for example, of the existence of protected areas. Different social parameters, so population density, maybe occurring interest of indigenous populations and cultural background, different mining stage history, and also different logistics, so in terms of accessibility and infrastructure. Comparable sites did not exist in Europe before that could be compared to that. Existing sites were either only the sites designed as a calibration site for a specific technique, or they missed the social and environmental evaluation aspects. Can you go to the next slide, please? The main goal of these reference sites was to serve as benchmarking sites for best practice to increase the confidence of decision makers, investors, and the civil society. Developers of, for example, of innovative exploration technologies should be able to come to these sites to test, benchmark, and certify their approaches, and not only for their technical efficiency, but also for their social environmental compatibility. The first important step was to create a database of high-resolution validation data and state-of-the-art exploration methods, so that we can achieve a full understanding of the geological processes that we have within these sites, and that also then allow the evaluation of new methods. The second important step of Infact was then to test and develop innovative technologies. So I listed here some directions that we went towards. So for example, to increase the resolution of some technologies. So for example, by going towards drones, so UAV-based magnetic and hyperspectral data, to increase the depth of penetration using, for example, low frequency EM, to lower the impact on environment and society by focusing on airborne methods or passive sensors, and also to explore new novel geophysical parameters that have not been extensively used for exploration before. So for example, airborne IP or thermal infrared hyperspectral data. And last but not least, it was also important to do not only the acquisition, but to also bring further the data processing and integration. So for example, that means that multi-source data can be interpreted in a really truly integrated way and not only as a joint visualization. I will show you on later what I mean with that. If you go to the next slide, I just wanted to highlight here that in a little more visual way, how these innovative data acquisition campaigns were performed. And important here to see is that we not only acquired data of the technologies that were developed by the partners, but that we could also attract further big players, for example, CGG, to test their technologies. And we also had a great chance to perform some cross-project campaigns. So for example, with passive seismic, as Nick, so with the Pacific project, as Nick also mentioned earlier, as you can see in the upper part of the image. If you go to the next slide, I would just quickly like to show you an example of some of these innovative exploration technologies. So you can see here the usage of hyperspectral data to analyze the mineral composition of the surface, which is a completely non-destructive and passive technology. And you can apply that from different scales and platforms, so for example, from planes, from drone, or from the ground. And within Infact, we could further develop this technology to use it up to a stage where the data can be really accurately corrected and integrated in a 3D environment. So this allows them to accurately map your mineralogy, correlate it compositionally with structural information, and combine the results with any other 3D localizable data sets. And this workflow was also combined in an open source toolbox that is also available online, and that is still under constant development. If you go to the next slide, you can see a second example that we've already heard a little bit on today earlier, on the geophysical airborne electromagnetic data, and which also greatly shows the power of these reference sites in terms of benchmarking and evaluation. So here we acquired, together with CGG, some innovative low frequency EM data over the reference site in Spain, in Las Cruces. And here this low frequency allowed a much deeper penetration depth of the signal compared to state-of-the-art systems. And as it was used on these reference sites, we already knew exactly the depth of the geological basement, So we could really validate these results and could prove that this novel low-frequency EM method was indeed able to penetrate below the basement boundary and could such map the underground way more accurately. If you go to the next slide, I would leave a little bit the technical aspects and elaborate a little bit more on how Infact finally attempted to shape a discovery roadmap for Europe. One important outcome of that process was to develop an index that should evaluate the risk of any exploration project in regards to the so-called social license to operate. This topic of social acceptance has been increased in focus and discussion in the last years, and is still related to many insecurities on how we can evaluate a project's social license to operate and how the actors can act accordingly to increase their chances. So as you can also see on the right side in this sentiment survey from this year, you can see again that these ESGs, environmental, social, and corporate governance issues, have been seen as the topmost risk for any operations in mining and metals market. If you go to the next slide, please. We have now, within Infact, tried to develop an Slo Index that has been designed to promote the certainty and illustrate some weak areas in a project that needs to be addressed. So it really gives, in a quantitative manner, it allows to take tailored actions to secure the social acceptance of a project. It has also the potential to use it as a communication tool for communicating the Slo potential to potential investors and stakeholders. And it is important, so this is like an ongoing discussion, and it is important that this Slo Index is further developed and discussed. And we hope to promote it also as a tool to policymakers and land use planners. If you go to the next slide, there's another important outcome that is shown here. That is a certificate scheme that was developed within Infact for novel exploration technologies. And it allows companies to get a quantifiable certification of their method's performance in terms of these ESG factors, as you can see on the current slide. Or if you move one slide forward, please, you can also see, no, the other direction, sorry. Exactly, thank you. You can also see that also the technical performance can be evaluated using the benchmark or reference sites that were established. And we have seen a very great demand and also an acceptance of these certification schemes by the industry and by technology developers, as it really allows to ultimately evaluate the benefits of innovative exploration technology over traditional techniques in both a technical and also social environmental way. If you go to the next slide, please. I hope I'm still somewhere in the time. In this framework to develop a discovery roadmap for Europe, Infact has also set up an exploration decision tree to set new standards in how exploration projects should be approached in the future. And the most important point to consider here is that the core point lies here in the early adoption and equal consideration of environmental and social aspects at all stages of the exploration. And in the future, it should be important to have earlier and more meaningful investment in these ESG issues. Has to be seen as an important way to reduce risk and also increase the value of exploration projects. Open questions that are still under consideration here are how these concepts can be included into established reporting standards. But the most important thing is that the discussion here has started. If you go to the next slide, please.
Sandra, 2 minutes.
I will try. There you can see also one of the most valuable outcomes of the Infect project, which is the Infact Portal. And it serves as a database for the test sites and integrates technical, geological, environmental, and social variables in one platform, and also adds some additional results from our external sources. So, for example, from the European Environmental Agency, and that should allow to explore potential issues with new projects or the accessibility of a resource. Yeah, so if you go to the next slide, you can see that, so I just show here some examples of the dissemination, outreach, and education part of Infect. So mentionable here is the large NHM event, Can Mining Make the World a Greener Place? That was organized in cooperation with the Natural History Museum in London and also with Pacific, with the Project Pacific. And here representatives from industry, research, nonprofit and governance were brought together on one table to discuss the future of mining. And it got a huge outreach. And the event started important discussions and also helped to set up a long-term dialogue between the stakeholders. If you go to the next slide, maybe I can cover that quite quickly. Another important aspect was also to transfer the results of Infect to the next generation. So we also organized, so here is shown a winter school, but there were also other activities where the next generation, so students from all over Europe, were trained not only in the technical aspects of innovative exploration, but also in considering environmental and social aspects into the exploration context. And if you go to my last slide, I would like to close now my talk with the vision that Infect had for the mining in Europe. So basically, we have a geographically and commodity-focused subsidized sector that is accepted and that also accepts that there are no-go areas that are, for example, heavily populated, protected, or of specific natural and cultural importance. That sets societal acceptability and inclusion in a focus from the outset. That also uses high-tech and innovative approaches over state-of-the-art approaches to reduce impact and increase the efficiency. I'm out of time reason. I don't want to read everything here. I just wanted to say that we have seen, like, from the results of Infect, that these ESG issues and aspects related to that got louder and louder, and that we have most urgently to consider them if we want to have a responsible minerals industry in Europe that is also acceptable, that benefits also the society, that meets the needs of the EU Green Deal, and that also contributes to the UN Sustainable Development Goals. And Infect has hopefully contributed to this goal in a variety of ways that are set up for further development. And most importantly, we have started the discussion. So thank you very much. That's it from my side.
Thank you very much, Sandra. Thank you for the effort for keeping the timeline right. So we have no question. Your presentation was very clear, straightforward. Impressive result also for the Infact project. Thank you very much. What I can say, the work on social acceptance is completely innovative, and the dissemination measures implemented during the lifetime of your project were really appropriate. So very good. So thank you very much. We have no question on the slide though. So as the other speakers, you may wait for the panel discussion that will be organized or will be held later on. Now we have the coffee break until 11:45. During this coffee break, please have a coffee, have a rest, but also if you can access Slido and post your question there, would be great to show your interest and ask the speakers the points you didn't get fully during their very clear presentation. Thank you very much. See you in a few minutes after the coffee break at 11:45. Welcome back after the coffee break, just a kind reminder, we had before the break the presentation from 3 projects focusing on exploration, mineral exploration. I mean Pacific, Smart Exploration, and Infact. And now we will focus on presenter representing Impact and X-Mine EU-funded project dealing with mineral extraction. I have some question in Slido, maybe to check before moving on. Maybe Sandra, may I ask you a question that was for you? Opposition to mining seems to be gaining ground. Part of the problem may be the negative image in the media. How can this be countered? Do you have?
I can really answer this. It's a complicated question because it covers a lot of aspects, and of course it's quite difficult to change a perception from one day to another. So what we need to do is we need to gain trust in sustainable and acceptable exploration techniques, and also trust in that these techniques are really truly applied in the way they are thought of. And that cannot only happen by promises or communication in one direction. There needs to be an open discussion on these topics. There needs to be a lead by example, definitely. There needs to be showcases that that new innovative technologies and also new approaches to include environmental and social aspects into the mineral exploration scheme, that they are really implemented, and that also the industry and the mining industry cares to implement them. So I would say that really communication is key here, and also that we need to accept that it will take a little bit of time for the, of course, first for the media, but also for the society to really accept this new us basically of exploration, and that we really need to earn this trust. So
Thank you.
I think we might also cover it a little bit later in the panel discussion.
In the panel discussion. Thank you. Thank you very much for this straightforward answer. That will be further discussed later on. So I will continue with the program. So I would like to introduce now the next speaker, Catherine Moore from University of Exeter. Catherine, or Kate, gained 3 qualifications in geology, experimental petrology and archaeology from the University of Edinburgh, University of Bristol, and National University of Ireland Galway. She led the magmatic study group at the National University of Ireland Galway from 1999 and moved to the Camborne School of Mine in 2012 as lecturer in critical and green technology metals. She participates in and supervises research relating to alkaline rocks, carbonatites, or deposits, particularly critical raw materials or critical metals, sorry, and small scale mining. She leads the project Impact. Please, Catherine, Kate, the floor is yours.
Thank you very, very much. Can I have the slides, please? Great. So the original idea behind the Impact Project, which stands for Integrated Mobile Modularized Plant and Containerized Tools for selective low-impact mining of small high-grade deposits. The original idea was that we would use this approach to try and reduce potential for shocks and price volatility that arise from demand-supply imbalances. And we would do that by increasing the rate of access, the speed of access to more local deposits. So we acknowledge that Europe has accessed its largest, highest grade ore deposits, but has lots of potential in small ore deposits. Next slide, please. So we took the approach that we want to access marginally economic deposits because of their size of any kind, including critical raw materials. And although we had this particular remit, we acknowledge that there is a wider conversation happening in the industry that small-scale mining may become increasingly important because of the carbon footprint of materials transportation across the supply chain, because in Europe we have very populous areas, particularly around heritage mining districts, where populations have developed for that reason through history. And we need a way of mining that's sympathetic to local populations. And also there's the problem of that the mining industry faces in accessing investment for high capital expenditure startup mines. So the 4 ways that we approach the problem are in this slide, that we need to know where those deposits are that might be accessible. We need the flexible strategies to accommodate the variability and the complexity of these types of deposits. We need to safely be able to put technologies in place, and we need to embed all of that in the local communities, because the relationship between small-scale mining and centres of population is a really, really critical one. Next slide, please. So the consortium we're working with is depicted there on the right. Essentially, we're an even balance of industrial partners who are mostly small and medium enterprises and research institutes, including a geological survey. And since critical raw materials are part of the increasing array of modern commodities that we need for the green energy transition, there's a very, very wide array of materials we need. We felt that adaptability and transferability of solutions was key, that we wouldn't be able to necessarily afford bespoke solutions for every single metal if we're doing low capex solutions. So we tested technological solutions at 2 different types of mine. One, a bulk metal mine, which was the lead mine at Olivo in Bosnia, and one at a critical metal mine, which was an antimony mine in Serbia. And we undertook work as well. Although we were focusing on deployments at these 2 sites, we needed to know what the wider potential in Europe was for other commodities and for other places. Next slide, please. So our partner in France, BRGM, undertook work to build a small deposit query tool, which is open access, freely available to any academic, any industrial entity that wants to investigate potential. So it's hosted on the Minerals4EU database, and it can very simply be accessed. And as you can see from the map there, there's a huge range in different commodities that actually meet the small deposit query criteria of scale and ore deposit grade. And there are ways to correlate across the nature of the deposit with the land use characteristics as well. And it's a really important way of accessing what's the potential for licensing. So we established that there is really very great potential for small-scale mining fairly close to home in Europe. And if you go to the next slide, please, we then sort of move on from focusing on what the potential is to how do we access those kinds of ore deposits. So we put in place containerized technical solutions, and we were very, very clear after a lot of discussion about those technical requirements and access to different types of areas, whether they're populous areas or remote areas, that the technical solutions should either be plug and play containerized solutions or containerizable solutions that can be easily unpacked and deployed. And we specifically focused on small containers, 20-foot containers, to reduce the lorry size to access even mountainous areas. What I've got depicted in this slide is the green underground cutting tool that's used at small scale for accessing steeply dipping subvertical vein type deposits where the cutting arm is also a shoveling arm and can move material back through the machine to a vehicle that can then transport material out, so that the drive can be very small as well. We then have an ore sorting piece of equipment in the picture below, which is fully containerized, with conveyor belts that connect it to everything else. And then the blue module there is a comminution circuit. So each of those two was just one 20-foot container. And then the bottom right figure D is the minerals processing test facility, which is a 4-container stacked deployment, which takes a few more days to deploy. The really important thing is that the cutting tool and the comminution units could be deployed in half a day. The ore sorting unit took a day, and the minerals processing units took several days. And in the background of figure D, you can actually see the full-scale plant under construction at the same time, which was taking months to deploy. And we could actually do that very, very fast with off-site construction and deployment to site. So the logistics were really, really important.
Catherine, 3 minutes left, please.
Okay, I will move along quickly then. Let's go to the next slide. So our deployment solutions were really important. We got everything on site at Olivo, where the site was fully licensed and environmentally licensed as well. For the Zajaca ore deposit in Serbia, we were not able to gain environmental licensing because of the lack of knowledge with our adaptable processing solutions. And so we had to operate in a satellite mining model there. So by default, we operated in 2 different mechanisms, one with everything on-site deployment and one as satellite deployment. Next slide, please. We also, because we have this modular approach, we were able to attribute the environmental impacts to the different unit processes of small-scale mining. And we did that with life cycle analysis using a functional unit of production of 1 ton of lead at the Olivo mine site. The really, really important takeaway messages is that we can identify the environmental pinch points for particular changes in the processing stream. But the really, really important thing was the energy consumption. Next slide, please. So what we have here was a renewable energy survey of all the containerized solutions that are available on the market. their physical land footprint, and how much energy they can supply. The really, really important takeaway message was that for this small-scale mining, depending on the duration of deployment, the renewable energy solutions were more cost efficient than any diesel-based solution. So we can quite effectively, with the small-scale mining solution, close the loop at the minerals energy nexus. We can produce the raw materials for the green energy transition at low carbon footprint. And next slide, please. So as it's all about the impacts and the interface between small-scale mining and society, there was a very significant piece of work done on social sustainability. And social sustainability was, the concept was reinvestigated for small-scale mining, particular to Europe. And what was really important is the level of regulation, the footprint, and the impacts that can be controlled in Europe. But the counterpoint to that is that the societal expectation from mining is large employment, and it's for duration of employment for a working lifetime. So we have a lot of work that's coming out, but I'll focus on just one small aspect of that with the next slide, which is that because we understood through our practice on mine sites what the employment characteristics and the training needs were, we were able to think about how the rollout of small-scale mining might actually contribute to employment. And we were initially very concerned that the employment levels would be too low to actually warrant or inspire a lot of social acceptance. But once we've crunched the numbers, we actually found that the employment characteristics are such in those deployment sites that the potential is there to reduce unemployment by between 5 and 10%, which is really quite significant. If I move on very quickly, I want to just talk about what's left, what's happening subsequently. So for our small and medium enterprise partners, the small-scale underground cutting machine has not been taken up yet by mining. It's actually been taken up by construction. And that's really important in that the mining community can be quite slow to change practice. And the investment patterns can be quite slow to change. So we need to find ways to keep these technical solutions available to the mining industry while we're in this period of adjustment. And so finding alternative applications is really quite significant. The next slide, please. The project has also allowed EPSA, who manage water quality, to create a new design for their business model, which is being rolled out as well. And the next slide, please. And we're currently at the University of Exeter trying to work on how we actually inspire more investigation and uptake of small-scale processing solutions. And the next slide. So I want to just put in some takeaway messages now. That the drive towards efficiency for the economies of scale drives innovation in the bulk metals production sector. It doesn't necessarily translate very well to the technology metals, but with the small scale production, we do have the potential to improve efficiency a little bit. We have the potential to stage production and generate some initial revenue for bigger plant. We have the potential to think about accessing populous areas. Yes, the next slide. Okay, so What we need to do, I think, is create more capacity to think about where we deploy small-scale solutions, how we integrate that in the supply chain in a very multi-layered approach. And we need to think about how bespoke solutions are appropriate to small-scale mining and how we balance the efficiencies of scale with our need to access ore deposits. And the very final slide is just a list of the outputs that are already available as peer-reviewed publications that I've mentioned just in this presentation here. Thank you very much.
Thank you very much, Kathleen, for this very clear presentation and for the work summarizing the work done by the closed Infect Project. So thank you very much. We will move to our next speaker, Jacek Kolacz. I'm sorry, Jacek. I hope I have pronounced your name correctly. Yes. You have obtained your Master in Science degree in 1989 at the Mining University in Krakow, in Poland. And then you received your PhD degree at the Norwegian Institute of Technology in Norway. From 1994 to 2003, you worked at SINTEF Research Organization at the Department of Material Technology as the senior scientist. In 2003, you founded COMEX AS, and in 2007, COMEX Polska, where you are currently working as the president of the two companies. You are author and co-author of over 100 papers published worldwide and many scientific reports on sensor-based sorting, fine particle, process control and instrumentation, simulation of mineral processes, plant design and optimization. You are also an author of many international patents related to material and mineral processing equipment. So please, Jacek, the floor is yours for providing us with insight on the result of the X-Mine project.
Thank you, Veronique. Ladies and gentlemen, I'd like to present yes, if we can start from this slide. It's the first slide, yes. I have a pleasure to present the results of the X-Mine project, which was actually titled as a real-time mineral X-ray analysis for efficient and sustainable mining. It was lasting for 45 months, and it just finished the last activities. So next slide, please. The consortium was from 15, it was in form of 15 partners, 15 organizations from 9 different countries, covering very nicely from the north to the south. We had Sweden, we had Finland as a coordinator. In Sweden, we had research institutions, universities, and also the mines. In Poland, we had sensor producers, in Czech Republic as well. In Romania, the universities, in Bulgaria, the mine, and in Greece and Cyprus, we had mines, 2 mines, which were performing research related to the sensor-based sorting applications. Next slide, please. The project was divided in different work packages. The most important is one in the upper left corner. It's 4 different activities where we had ore deposit modeling, 3D modeling of the mines. We had a sensor and data fusion development, where we were actually developing sensors as a dedicated sensor for the technology, for the chosen technology. We had online analysis and sensor-based sorting performed in different scales, laboratory and pilot scale. And finally, the prototypes were installed. I think we are a little bit, yeah, if we can go back, sorry, thank you. In the work package 4, we had the prototypes which were actually tested in the mines in the work package 5 in 4 different mines in form of pilot units. And next slide, please. Normally, when we talk about the pre-concentration and main benefits, we consider the traditional solutions like we have on the left side of the slide, where we have the mine, we have a processing plant, which then generates a certain product and the waste. And then we can consider the next slide, please. The advantage of using the sorting process in the basically in between the processing plant and the mine, where we can remove the waste material in the early stage. So if we can see the advantages, it's a removed impurities in the early stage. Then if we can go next, the impurities are in form of large particles, which can be applied to different purposes, like road building, for example. Then the next one, we have the reduced transportation of the processing plant to the processing plant, which is very important. Then we have the lower processing cost by reduction of the grinding process, flotation, filtration, drying, all energy and CO2 emission behind it. And then we have the product quality, disposal, of course, reduced waste and disposal, and the increased quality of the final product. So this results in the huge reduction of energy and lower energy consumption for the material and per unit of the material. And obviously there is a reduced footprint, carbon footprint and emission of wastes. Next slide, please. Yes, the project included the modeling of different drilling technologies, which could allow us to have the 3D image of the mine deposit in a form that we could perform the optimal sorting or optimal further concentration, pre-concentration. On the next slide, we could see the main pathway for the 3D modeling, starting with these arrows from the 3D model, going through the property stage, state equations, numerical simulations, decision making, until we achieve the final economic image for making a final decision and planning. Next slide, please. So as a result, we could see, as on the left, we could see the block showing the local image of the concentration of different metals and the position in the deposit. And then finally, we could see, like on the right picture, we could see the whole mine in form of different blocks, which we can separately treat during processing and mining process. Next one, please. The main objective was to develop different sensors for exploring the materials and minerals in a better way. And one of them is the drill core analyzer, which is allowing us to analyze very quickly and very efficiently the composition of the material we are extracting. And the principle is shown on the left, where we are using the different technologies. It's X-ray transmission, X-ray fluorescence for analyzing the core in the very precise way. On the right side, we see how it looks in reality. And the next slide, please. This is actually the most important part. Is the image from the analysis. On the left, we see the drill core during analysis. In the center, we see the fraction of the chosen part of the drill core, and on the right side, we see the table of elements which were detected. So we could also combine it together, so we can see the compounds or minerals directly during the analysis. So this is a very important picture because. As on the left side, we see the composition of the drill core. So once we analyze the whole deposit this way, we are able to simulate the concentration and the dissemination level of the mineral. So at the end of the day, we know which part of the deposit is good for sorting, which is sortable, and which part is completely impossible to sort because we have a very highly disseminated material. So as a result, we can achieve the very important parameter in the very early stage of the deposit exploration, how we can approach the whole deposit in an optimal way. So next one, please. The result of one of the objectives was to install the sensors in the same part of the in the laboratory scale, in the same machine, on the same sorting machine, where we could compare it with the standard sensors, like we can see on this image. It's a installation in Poland at COMEX, where we have all combination of possible sensors existing today, and comparing it together with comparing them with the Xmind sensors developed during the project work. So we can see in addition to the standard sensors, we see on the next one, we see the multi-energy sensors, which are X-ray transmission. It's a different technology. It's maybe not so important. And the next one, please, is the high definition sensor, which was developed in the Xmind project. Then the next one is the RGB 3D cameras, which are investigating the surface and the texture of the mineral. And finally, the collimated XRF, which is able to tell us the composition, chemical composition of the minerals. And all of them are compared at the same time in real time. And in this picture, we can see that the discharge belts on the bottom of the picture, they are mixed together, and then the material is sent back to the input of the machine. So we are able to circulate in the very high capacity, close to 50, 100, 150 tons an hour capacity, so corresponding to the real scale. And we are able to adjust the sensors. And then when we are finally ready with the sensor settings, then we can reverse the belts and we achieve the separation on the other side of the sorter. It's not shown here, but it's a very effective way of optimizing the sorting process. And next one, please. This technology was then applied to on the left side. This is just a schematic picture of the sorting process, where we have the X-ray units, we have the different cameras and different sensors. Then we are using pneumatic nozzles to reject the material which is we are not interested in, or opposite, if we can also reject the waste, we can reject the product. The point is to separate them to the separate belts. And then on the base of this, we built prototypes. Sorry, too fast. On the bottom, we see the container-based solutions, where we have, during the project, we constructed 2 of such containers, which could be moved from mine to mine for high scale, for large scale operation. Okay, the next one, please. Here is the difference. We are just interested in investigating the composition of the rocks in a very accurate way. So this is the comparison of the standard sensors, which we can go further. Here we can see the X-ray image based on the standard X-ray transmission sensors, which is actually telling us something, but it's not very accurate. It's not with a high resolution. When we use the sensors which are on the just shown in this lower right corner, we achieve a completely different image, which is on the next here. Yes, this image shows us the very high resolution composition of the same rock. But we are able to see the clouds of different particles. We can see even single particles with down to 50 microns resolution. So it's a completely different approach. We are able to see very low concentrations of metals, for example, in ores like copper ore, which is normally not possible to be separated by standard sensors. Next one, please. So as a result, I would like to show you the foreground of the project. Here is the picture of different particles which are detected, and every particle during sorting is described by different parameters. This happens very fast. We have about 10 to 20 milliseconds to describe each particle. And on the base of this, we are able to build a grade recovery curve, which we can see on the right side. It's just the curve showing on the horizontal basis the mass recovery from the process, and on the vertical axis is the ore recovery, so metal recovery. So when we start from the top corner, top right corner, we see 100 and 100%. So this is no sorting. And then when we move down with this curve, we are able to see, for example, when we choose on the horizontal basis axis 0.6 or 60% recovery, this corresponds to about 98, 97% of the ore recovery. So that means by reducing the main mass of the material going to the processing plant by 40%, we are just losing 3-4% of the metal, which is actually very hard to recover anyway in the flotation process. So it's a very efficient situation. So we are able to evaluate this kind of sortability for different mines, for different minerals, as shown by different curves on this image.
May I kindly ask you to conclude so that we keep some time for the discussion?
Yes, my last slide on the next one. It's just the image of the sorting unit in one of the mines where we eliminated 22% of the waste rock, which was unnecessarily processed in the past. And the next one, please. Next one, please. Here is just a example of the potential for a typical copper ore mine, which is producing 30 to 40 million tons a year. And we are able to eliminate in such a mine up to 10% of the waste rocks, which will result in the next one, please. Reduce the wastewater by about 10%. The next one, a 10% reduction of flotation agents. The next one, reduce the waste, flotation of waste by 10% as well, which is corresponding about 3 million tons a year. Reduce electrical energy by 100 million kilowatt hours per year. And then we reduce the energy cost, obviously, about 10 million euros per year. And then we reduce the CO2 emission, about 30,000 tons a year. And finally, no impact, no negative impact. So absolutely win-win situation. Okay, and that was the last slide. Thank you very much for your attention.
Thank you very much. Thank you very much, Jacek, for this very nice presentation. I will go to my colleague Marko Cacanowski, who will take over now and moderate the panel discussion. So Marko is project advisor at ADEA in the unit industry, and he monitors EU-funded project as we all do, and his projects are predominantly related to mineral extraction area. Please, Marko, it's your turn. The floor is yours.
Thank you very much, Veronique. I hope you can hear me.
Yes.
Okay, thank you. Thank you again for kind introduction and for managing successfully this morning's session. Colleagues, to begin with, I would like, first of all, to give my thank you to all the speakers of this session. And I must say the presentations were very exciting. And thank you also for taking some of the questions from our audiences. I would like to open now the panel discussion on securing the supply of primary raw materials in a sustainable and responsible way. Please also be informed that I took note of some of the questions received via Slido in the meantime this morning, and I will do my best and make an attempt to incorporate Slido questions in one of the following questions I will have for the panelists. My proposal is that we start discussing some issues related to technological innovations that your projects have developed, and for example, we can take the example of Pacific. Pacific uses passive seismic method to provide useful background information about geological characteristics in mineralized region. And I have a question for Nicola. To what extent do you think, Nicola, passive seismic methods will be useful tools for mineral exploration? And what are the major advantages and disadvantages of this method? Thank you very much.
Okay, well, what are the advantages? We'll start with those. It's low cost. It's relatively low cost compared with other methods, and low impact on the environment. You know, we don't need roads. We don't need to bring in heavy equipment. The disadvantage, the main disadvantage, is the relatively low resolution we get using the traditional surface wave tomography. We tried several ways to overcome this advantage, and we heard other one mentioned as well in the other talks. Particularly important, I think, is the slimline sensors, which can be put down drill holes, and I think by using those in collaboration with a surface wave array, a surface array, we can get around that problem. Mentioned quickly, there are various applications in mineral exploration. Particularly important is the technique is very useful in mapping the thickness and characteristics of the glacial or younger sedimentary cover found in many areas.
Thank you very much, Nicola, for your answer. I would kindly have a question for Jacek Kolac that represents the project X-Mine. We know, Jacek, that one of the X-Mine's key innovations is in the field of sensor-based sorting, where you are a prominent expert. Sorting technologies were not very popular so far. Why and how do you think that X-Mine project could change that?
Yes, it's a very good question because it's basically the sensor-based sorting equipment was not very popular due to the low reliability of this equipment. And as we know, as we all know, mining is a traditional industry. They need very robust and reliable equipment. So the new technology has basically helped a lot generally to be more reliable. And this is a very important part. How X-Mine could contribute? Well, it's a development of the new sensors. Basically, when we know more about the sorted material, the better result we can achieve. So the main issue is the loss of materials or minerals in the waste fraction. So normally when we sort or pre-concentrate the material, the waste fraction is a lost fraction. So if we lose the valuable material there, then we lose everything in the process. We lose a lot in the process. So it's very important to take care of this fraction, this material, and the X-Mine sensors allow to eliminate these losses, and this is a very important parameter. And of course, finally the treatment, as in X-Mine, we treated the whole problem in the holistic way. So it was from the excavation to the final generation of the concentrate and the waste fraction as well. We were looking also at the waste, how it looks like and what it means. So we could see not only the economic impact, but the environmental impacts.
Thank you very much, Jacek, for your answer. One of the projects presented this morning is Smart Exploration. And we know that Smart Exploration is a large consortia consisting of 27 different partners, some of them small and medium-sized enterprises, academic institutes, research institutes, 4 major mining company, and also civil society organizations. So I have a question for our panelist, Valentina. How did you manage the relationships in the consortium and the collaboration, which how it went? Can you please give us your experience?
Thank you very much. Well, the consortium was really broad, both in terms of numbers and in terms of kind of partners. I think that the key was, apart from, of course, a very active management and a very active internal communication structure of the project, but the keys were 2. First of all, we were all in love with scientific and technical development, and this was kind of glue that kept us together. But the other important thing was that since the very beginning, the focus for all the partners was on innovation. So there was a clear common goal of having to produce very clear and concrete results that might bring products and methods to the market. This was a very good way to manage the relationship within the consortium, because the research institution cooperated with the enterprise world, having a common goal. So we had very clear since the beginning that innovative doesn't mean novel. It means something that can bring innovation to the market. And this was very well accepted both by academic and research institutions and, of course, by companies. The different, let's say, expertise went together very well. The goals were very clear, and the consortium really, all the partners learned from each other. And I think the cooperation was, in this sense, extremely productive.
Thank you very much, Valentina. If you allow me, I would like to open a new group of questions that deal with considering the innovations of your projects from the angle or perspective of their potential for industrial application. And just to make a bridge between the previous question and the new question, Valentina, what was the major added value for mining companies participating in the Smart Exploration Consortium?
I think that mining companies had two main positive outcomes from the project. The first and more obvious one was the extension of the knowledge about their targets. Let's say we extended significantly several mineral deposits in terms of knowledge, geometry and characteristics of the deposit. So that was a kind of direct advantage for the companies. But the other one was certainly to be exposed, particularly the young professional people who participated to the project, also from mining companies, to be exposed to innovative methods to deal with their exploration plans. And I think this has opened up to new opportunities also for their future investment in exploration.
Thank you very much, Valentina, for your very clear and straightforward answer. I have a question for Sandra, a representative of Infact Project. Sandra, in what way can Infact solutions contribute to the implementation of novel technologies in the mining industry? Could you give us, please, a few examples? Thank you.
Sure. So I think, or we at Infact think that it's fundamental to transfer innovative technologies to the industry so that we can really achieve a sustainable exploration. And two important things that Infact could contribute in that sense is first to have a strong and direct involvement of the mining industry, so within the project. So as a partner and also within the discussion rounds that were taken, but also in potential follow-up projects and in all the discussion rounds that were done. And the second thing, and I think that's also very important, is the establishment of these reference sites, because they can serve as a permanent infrastructure to test and demonstrate innovative technologies, so they can help also to gain the trust and to really benchmark the performance of these new technologies in a real case scenario. And they can also serve as case studies and narratives. So companies are able to directly promote their technologies to the mining industry on a concrete example.
Thank you very much, Sandra, for your answer. Coming back to X-Mine's sensor-based sorting, Jacek, what is the potential of this concept on the world global market, including other minerals, for example?
Well, the potential is huge. There is a absolutely advantage of using sorting in almost all mining areas. It depends, of course, on the geology but basically, we have two major applications. One is the pre-concentration, so that means we remove the waste in the early stage, so we don't need to process it and grind it and have deposits in the form of fine particles. But also there is a possibility to put it inline in the process at the processing plant. So we could, for example, divide materials in different groups so they can be treated by different flotation approach, for example, a different separation or processing approach. So this is a very important application, which is also now having a more wider applications. Regarding the general advantage is huge because it's a win-win situation on all aspects. Basically, there is always a kind of compromise or trade-off between the economy and the environmental impacts. In this case, we are actually going in the common direction. So it's a win-win situation regarding the economy, product quality, and also environmental aspects.
Thank you very much, Jacek, for your explanation. Now we are moving from this industrial impact to the field of environmental benefits. I kindly invite representative for Impact Project, Kate, to let me know what she thinks about that. There are estimates that the transport of mineral resources emits as much carbon as does the industry. And Kate, how could we think more carefully about raw materials production as a function of material transportation, that is shipping, for example? And how do we frame this globalization, localization debate in the context of responsible raw materials production?
Yeah, it's a big question. At the start of today, in the introduction, the supply chain bottlenecks and disruption due to shipping through the pandemic were highlighted. So we're used to thinking along our supply chain about where are pinch points and concentration of production and concentration of manufacturing, but shipping itself is a pinch point, both in terms of logistics and in terms of the environmental impacts. And at the moment, we've got really good understanding with a load of EU projects of supply chain characteristics, for example, with the battery raw materials and processing solutions. But we haven't necessarily included all the shipping impacts in those supply chain considerations. So on our own Impact project, we designed the project about reduced removal of materials and reduced transportation of materials on site, a bit like Xmine did as well. But the life cycle analysis focused on the functional unit, which was one production of lead concentrate on site. And we acknowledged that the energy benefits that we identified didn't adequately draw in the wider value chain issues. So that's one side of it. There's also a large focus on vertical integration in battery supply chains, things like that, to reduce impacts. And that vertical integration is not necessarily spatially constrained. It's not necessarily regional. It can be about multinational supply chains again. So the localization, globalization debate hasn't really reached that. So what is needed, in my opinion, is extension of life cycle analysis to cross-reference interventions in extraction and processing of materials with shipping volumes and flows with the impacts of freight. I also think we need to understand the impact of increased regional production in Europe, for example, and other parts of the world on the development of nations that are currently dependent on raw materials production. We could reduce shipping by increased vertical integration in those nations that are suffering the resource curse, and by centralizing some parts of the supply chain in those countries, we can actually make significant inroads with the Sustainable Development Goals as well.
Kate, thank you very much. We are going towards the last round of questions that deal with public acceptance and trust. And evidently, public acceptance and trust in raw materials production is essential for the execution of a project, but also for the rollout of project developments, of innovations. And Nick, I have a question for you. In terms of local community acceptance, what can be done to improve the trust of local communities and to better inform them of the need to produce metals?
Well, very quickly, the survey that was undertaken by the group in Dublin showed that there are two main conclusions: that the information has to be passed more effectively to those communities, and that the question is, how do you do it? It seems the one conclusion they came up with, that you have to stress more the benefits of mining, the benefits to local communities, stress that mining can be done efficiently. In Europe, mining can be done efficiently with relatively little impact, negative impact on the environment. And the information should come from reliable sources, which are government organizations, geological surveys, Eurogeoscience, and so on.
Thank you very much, Nicholas, for your answer. And certainly we have heard today many thought-provoking views. Thank you very much for this. I think that we could keep on discussing, but we are reaching the end of the morning session. I would like to thank all panelists for their valuable contribution to this discussion, as well as the audience for their attention and some questions. enjoy your lunch break, and we look forward to welcome you again for the afternoon session, which focuses on secondary resources, waste processing, and recycling schemes. Thank you very much, and it was a pleasure to be here today.
Thank you very much.